Hypothalamus Artificial Intelligence, HI, and Research Center for Advanced Decision Technologies, RCADT, presents the conference. Prognostic and Health Management. PHM, Prognostic and Health Management. PHM, or Prognostics and Health Management, is an engineering approach that uses sensor data to monitor the condition of a system, predict its future life, and optimize maintenance. It integrates technologies to detect anomalies, diagnose the root cause of faults, and estimate the remaining useful life of components, rule. The goal is to enable condition-based maintenance, CBM, or predictive maintenance, PM, to improve safety, reliability, and efficiency while minimizing costs and downtime. It is a comprehensive approach that uses insights from prognostics and diagnostics to manage system health and reliability through informed maintenance decisions. The key components of PHM are: Prognostics predicts the future state of a system and estimates its remaining useful life, RUL. Diagnostics identifies the root cause of a fault or anomaly. And Health Management, a comprehensive approach that uses forecasting and diagnostic insights to manage system health and reliability through informed and optimal maintenance decisions. Asset Management. The decision on the type of maintenance to be carried out depends on the costs associated with each possible methodology. The figure shows the associated costs, based on the expected value of the failure events. These are preventive maintenance, condition-based maintenance, and corrective maintenance. The total maintenance costs due to the methodology result from the sum of the direct cost of maintenance and operating costs due to failures. Preventive maintenance generates the lowest cost due to failures, and at the other extreme, corrective maintenance generates the highest cost. The decision problem is to find the methodology that minimizes the total cost. Condition-based maintenance, CBM. It's no surprise that the idea of efficient maintenance algorithms, originally motivated by strict emissions regulations and now driven by safety, logistics, and customer satisfaction issues, has culminated in the so-called condition-based maintenance, CBM, program. CBM consists of two main tasks, diagnosis and prognosis, each of which has provided the challenges to scientists and engineers in various fields of industrial engineering. Forecasting is concerned with predicting the remaining service life, future condition or probability of reliable operation of a piece of equipment based on the condition monitoring data obtained. This approach to modern maintenance practice promises to reduce downtime, spare parts inventory, maintenance costs, and safety risks. Given the importance of forecasting capabilities and the maturity of condition monitoring technology, there has been an increasing number of technological research and developments in machinery forecasting in recent years. Improvements in computational resource technology have helped engineers by introducing more powerful computational resources to make some aspects of these new problems treatable. In addition, it is even possible to leverage the information of the connected asset using cloud computing. Before the presentation of the asset management theory, the following key concepts are defined. Asset, basic unit that an industrial activity can perform. It is composed of multiple components. Example, a truck, a crane, a generation turbine, a transformer. System, a set of assets that, working in coordination, are used to achieve a company's production goals. Example, a power plant, a train. Subsystem, divisions of the system into groups of assets according to their similarity or their joint activity. Example, truck fleet, production lines, which are part of a broader productive system. Component, basic unit that makes up the assets. Each component can fail individually and be related to other components. Example, the tires of a truck, a cylinder of an engine. Asset network, connectivity of assets within a system or subsystem. Your activity should be planned together. Example, a set of generation units in a power plant, a fleet of trucks. The technological trend of PHM methodology is to produce closed PHM systems coupled to specific components so that they perform all the PHM processing necessary to control the component in a distributed manner. This is possible thanks to the computational power of supermicrocomputers, edge computers, that can perform complex processing and whose size makes it easier for them to be part of the industrial asset as measurement and data processing processors. A closed PHM sensor is a system that it is a set of one or more different sensors. Acquire and transmit data. Process and analyze data. Store information. Incorporates ability to solve local operation problems. The figure presents the case of a PHM system in the railway industry for the diagnosis and prognosis of bogie health. The bogie is the most important and complex integrated part, network of components, of the rolling stock in a train. It is responsible for fundamental functions such as support to the body, transfer of braking and traction forces, stability of the train at high speeds, safe passage of the railway curve and a good and comfortable ride. The main components of the bogie are bogie frame, axle set, suspension systems, primary and secondary. The final idea is to have industrial equipment, such as a train, that has PHM components, such as the bogie, to execute autonomously and in a distributed way the PHM process to protect the train and passengers from serious failures that imply the interruption of the PHM component network and, therefore, from the negative impacts that this entails. Artificial brains are backed by the technological capacity of computing. It is traditional to associate mathematical modeling with large-scale computing, which today is linked to cloud computing, integrated by supercomputers of bits, and by the birth of quantum computers, which are the beginning of a new era. But at the level of industrial equipment maintenance, network integration happens at the level of cloud computing, or core computing, and edge computing. The central computer with the control software can be in the wagon that controls the train, or in the cloud. The course introduces the integration of predictive analytics and prescriptive analytics to produce optimal maintenance plans. The image presents the three layers of PHM. Physical data twin interaction. The image presents the three layers of PHM. Physical, data twin, and interaction. The total time is divided into three parts: training, validation, and prediction. The historical dataset is divided into two parts: training and validation, composed of training dataset, part of the historical sample used to train and calibrate the mathematical model, and test dataset, part of the historical sample that is not used to calibrate the model and is used to check the quality of the model. And the forecast period, in which the model will be used to predict new samples. Equipment condition-based maintenance, CBM, represents the evolution of practice from reactive to preemptive engineering, having passed the following stages over time. Repair/replace when broken. Reliability-centered maintenance, a systematic approach to ensuring that assets continue to do what their users require in today's operational context. Enhanced diagnostics, process supported by why a component has failed. Condition-based maintenance, predicting the future state of a component so that maintenance is performed based on the actual condition of the component. The relationship between CBM and mathematical models is fundamental. Electronics are the cornerstone for the successful deployment of complex systems. Mean time between failures, MTBF, numbers alone are not enough. There is technology to identify systems that are degrading before they fail, support operational readiness objectives and cost-benefit based management initiatives. The steps of PHM correspond to observing, analyzing and finally acting accordingly with the aim of predicting the occurrence of a known phenomenon, the failure, instead of trying to understand it once it has occurred. The articulation of PHM components can be explained as follows. The purpose of screening is to identify the health status of the system, in good or defective conditions. When a fault is detected, the diagnosis allows the damaged component to be isolated and identified. Forecasting seeks to project the state of the system into the future. The PHM cycle includes 7 steps. Data acquisition, data processing, status detection, diagnosis, prognosis, decision-making, and human-machine interface. For example, for PHM, several monitoring technologies can be implemented in wind turbines: vibration analysis, acoustic measurement, lubrication oil monitoring, infrared thermography and visual inspection. These technologies can be classified into two categories of monitoring: continuous and periodic. Continuous monitoring techniques are widely recognized by the industry as beneficial but economically expensive, especially for onshore turbines. For offshore turbines, continuous monitoring is almost self-evident, and its increasing level offers an important opportunity for the industry to reap the benefits of PHM and reduce operating and maintenance costs. A description of a continuous monitoring system is presented in the figure. The steps are: get to know the industrial equipment, a wind turbine, high-speed shaft bearing, equipment to watch, bearing degradation, measuring system, bearing vibration trend from rain to failure, data processing, assets health indicators, evaluation of the condition, and bearing prognostics. Then, PHM steps are: sample data series that can be continuous variables, analyze data series and convert them into equipment states. The summary of the first part is: take data from the measurement system, classify and clean the data, and analyze the condition of components. The new figure presents the dynamic evolution, from T to T plus N, of the PHM process. A key part of the system is the human-machine interface. The PHM predictive process is composed of three stages: anomaly detection, evaluation of the level of degradation, and forecasts of the remaining useful life, rule. The rule is defined as the difference between the current moment and the time until the next failure. Advantages and disadvantages of modeling approaches. There are three modeling approaches to prediction: physics-based models, data-driven models, and hybrid models that combine physics-based and data-driven models. All three of these approaches are used in industry. Physics-based models, based on differential equations that deterministically describe physical processes. It requires experience in process modeling. It cannot be implemented with the data-driven model alone. Data-driven models, based on data taken from historical series. Easy to implement, as they do not require simulated operating conditions. Hybrid models, which mix the two previous approaches. It requires knowledge of hybrid modeling techniques, such as the Kalman filter. Model-based, physical, the degradation process that leads to failure is described from mathematical models of equations, differential or algebraic, derived from the physical system. The mathematical formulation is combined with condition monitoring data to identify the model's parameters and then used to predict the future evolution of the health status of the components. Model-based approaches are more accurate than others and have a long-term rule prediction horizon, but they require the scientific knowledge of an expert based on an understanding of system dynamics. Modeling real physical systems is challenging due to the complexity of real industrial systems and the stochastic degradation behavior of the component. Data-driven, based on data collected by installed sensors rather than building physical models. Data-driven approaches can be easily applied to prediction problems and require more computational time than model-based approaches. In these traditional prediction methodologies, the results of multiple algorithms are compared and the best one is selected for predicting the health status. A set-based prediction approach that combines multiple algorithms is also used to increase the likelihood that the methods will be used. The accuracy of data-driven approaches depends largely on the amount of data available. Probabilistic methods, algorithms based on machine learning, ML, are used. Example techniques, among many: regression analysis, artificial neural networks, Bayesian updates, and vector support machines. Hybrid, both model-based and data-driven forecasting approaches have their own merits and limitations. In principle, neither of the two prediction approaches is superior to the other. An example is the state estimation methodologies, the best known being the Kalman filter and all its variations. These methodologies date back to the 60s of the last century. The hybrid prediction approach is the current one, as it integrates the merits of both approaches while minimizing their limitations, so there is a clear trend for the integration of the Kalman filter with the ANN for predictive analysis. It is therefore important to note that the superiority of forecasting approaches can only be specific to each case. The second part of the PHM process must be the optimization of maintenance decisions. In summary, the PHM process is summarized in the three stages: predictive analytics, signal processing, and diagnosis and prognosis. Prescriptive analytics, maintenance scheduling. A key limitation of predictive maintenance models is the assumption that sensors always provide correct measurements. Faulty sensors can provide inaccurate measurements of monitored physical parameters, affecting the performance of PHM algorithms by transmitting inaccurate or misleading information about the actual state of the system. Measurement also affects the accuracy of the meters, which affects the perception of the system. This can lead to false alarms, resulting in useless trades and large financial losses. They can also cause false successes that end up putting the failure system at risk. For example, cross effects are known to propagate anomalous monitoring data from a faulty sensor to other healthy signals, making it difficult to choose the appropriate maintenance action. Fault detection is done by validating sensor data and has been addressed using different predictive analysis methods, such as support vector data description and plane-based one-class support vector machine. Diagnosis corresponds to the analysis of data from the past, and prognostic corresponds to the prediction of the future, in terms of estimation of the rule. Traditionally, PHM approaches essentially extrapolate trends based on recent observations to estimate remaining useful life, RUL, and end of life, EOL. Without understanding the uncertainty measures associated with the calculation, rule projections have little scientific value, as traditional approaches are largely qualitative and focus on few indicators at the end of the design's lifespan and even when the asset has exceeded its life expectancy. It is the understanding of the corresponding uncertainties that allows the development of a realistic business model that responds to the requirements of forecasts. Below are important mathematical relationships related to the estimation of rule processes, EOL, and other related variables. Experts must provide a detailed assessment of the failure behavior of machines and their components to maximize the level of accuracy in predicting the next failure time. This analysis usually results in so-called bathtub curves that show that a component of an asset presents a high risk of failure right after installation, due to installation errors or incompatibility issues with other components, and after its normal operating interval, due to degradation and/or natural wear and tear. Between these two phases, the machine must function properly, and its probability of failure is low and constant. Rate degradation depends on environmental and operational conditions. Monitoring usage would provide a margin of safety if actual usage is heavier than anticipated, red region, T1. The shelf life may be extended beyond the normal replacement time if the actual intensity of use is known, green region, T2. The rule is affected by the trending factor alpha, which increases its volatility as time goes by. The figure shows the evolution of the asset's health indicator, high, and the rule forecast. As a function of time, high indicates the level of damage at any given time. Rule can be defined as the period between the current time and the time when degradation will reach a threshold of failure. The trend factor increases the volatility of the rule over time. The rule estimate at each point in time must be characterized by its probability distribution function, which decreases as the EOL estimate evolves over time. Rule volatility disappears when the equipment's useful life ends. Asymmetrically, the volatility of the degradation state increases over time and affects the failure threshold. The image presents the diagnostic and prognostic process from the moment the measurements are taken until the prediction of the rule is made. The curve ends at the end of the asset's life. From the moment TP always initiates a new prediction, the volatility of which increases as the prediction horizon of the rule increases. An asset consists of numerous individual components with different lifetimes, so applying a single extension of useful life, EUL, strategy for each component does not provide optimal results. Recently, advanced analytical methodologies have been proposed to estimate the rule of assets equipped with modern sensor systems, which are supported by real-time models throughout the operational life of the asset. OIL is conceptually directed at the component, unit, or subsystem level. However, to be optimal, a decision must be made with all components in mind. This approach is beneficial for asset owners and maintenance engineers because it intertwines justifications into two categories: technical and economic. The technical side includes the safety, reliability, and availability of the asset, while economics looks at the return on investment, ROI, total life cycle cost, LCC, and benefit to cost ratio, BCR. The key is to understand that a degrading asset requires a different approach to operation and maintenance, OWN. An overall asset can be grouped into different systems, subsystems, components, and parts, so that the impact of degradation on the overall asset can be assessed at any of these levels. Assets are considered to have reached their EOL when a performance or degradation threshold is reached. Traditionally, these thresholds are typically determined using classic statistical approaches such as accelerated lifecycle testing or, in more recent times, the use of run-to-fail data and machine learning, ML, algorithms. Another way an asset reaches EOL is through obsolescence, when the asset becomes unusable and therefore economically and functionally impractical to operate and maintain. Maki et al., 2018. The analysis focuses on assets that have reached or are close to their end of life due to degradation, and are therefore repairable, replaceable, or non-repairable. From a PHM context, oil essentially restores an asset's condition indicator from a ready-to-fail state to a healthy or good state. However, it should be noted that it is common for the extension of the useful life to depend on how many times this extension has been carried out. Alternatively, an optimization model can determine the optimal lifespan by considering the economic value it produces, and not just statistical characteristics. Below, different life extension strategies are presented with their meanings and possible application cases. Replacement or repowering, as good as new condition, AGAN. Reconditioning, returns the equipment to a better condition than before, but not at the level of AGAN. Repair, applicable to components or subsystems of a more complex asset and is typically carried out using new or existing parts. Remanufacturing, attempts to restore a system to the original equipment manufacturer's, OEM, functional specification with warranty. Retrofitting, this involves replacing old components or equipment with modern equivalents. Use up, this involves using a component or equipment until the end of its economic life. Refurbishment, applicable to components, equipment, or systems to bring them back to a higher level of functionality. Reclaiming, applicable to systems that require regular lubrication or maintenance during their lifetime. Retrofilling, applicable to systems that require regular lubrication or maintenance during their lifetime. The figure shows the impact of single and multiple oil actions on an asset. Two periods stand out: original asset life and additional asset lifetime gains due to good maintenance actions. These actions are L1, in green, and L2 in blue. Accelerated life cycle testing, ALT, evaluates the reliability of the product by subjecting it to extreme and above normal conditions, resulting in faster failures than would occur in real life. The methodology involves applying higher stresses, such as changes in temperature, vibration, and humidity, so that manufacturers can identify design flaws, predict performance, and estimate the lifespan of a product in a shorter time. This allows for better product design, faster time to market, and more accurate reliability predictions. In the diagram, this phase is related to accelerated aging, an additional stage of the PHM process. The data obtained from accelerated aging are converted into degradation parameters, and the prognostic phase is applied to determine the rule and EOL. To measure the effectiveness of PHM, it is proposed to choose one or more performance metrics. Saxena et al., in 2008, proposed the following: Prognostics horizon, accuracy, relative accuracy, cumulative relative accuracy, and convergence. Alfred North Whitehead affirmed, algebra is the intellectual instrument which has been created for rendering clear the quantitative aspects of the world. Thank you for your attention.